Yeah. So today we will discuss about the applications of direct sequence spread spectrum signals. Okay. In that, first one is low detectability signal transmission. Okay. That is the first one what we are going to discuss. So here, what we think that is what low detectability signal transmission means. As I said already, the characteristics of the spectrum signal is what it is possible to hide the transmission of the signal, right, at a very low power, so that the other fellow will not be able to detect it, right? So let us see how that is done. So the signal is transmitted at very low power so that the listener trying to detect the presence of that signal will encounter in a difficulty in doing so. Okay, means you will not be able to detect it. Means the unintended user will not be able to do that. Let us see how and all in detail. Then another application is the multiple access radio communication. In that, specifically, we are discussing about CDMA, that is a code division multiple access. And the third one is the communication over channels with multipath. Okay, of course, you may be aware what is multipath. If not, also we will have a discussion on that. Then it is used in wireless local area networks also. Okay, so let me take up the first one, that is low detectability signal transmission. So here what happens, the information bearing signal means the message signal is transmitted at a very low power level relative to the background channel noise and as well as thermal noise. Okay, so this thermal noise is generated in the front end of a receiver. We all know that, right? So we are going to transmit our message signal at a very low power level. Okay, and that power level will be very small compared to the channel noise and as well as the thermal noise which is generated in front end of the receiver. Okay, so we know that the direct sequence spread spectrum signal occupies a bandwidth of W, right? So W hertz we say. Then the power spectral density of the additive noise, which we say it is N naught, right? Watts per hertz it is. Okay, don't think that it is W by hertz. It is a N naught is what watts per hertz. Then the average noise power in the bandwidth W is denoted as the average noise power is denoted as P suffix N, which is equal to W into N naught. W is the what? Bandwidth of the spread spectrum signal, and N naught is the power spectral density of the additive white noise. So the average noise power in the bandwidth W is equal to what we can say, which is equal to W into N naught. So the average received signal power, okay, at the intended receiver is denoted as P suffix R. Okay, the average received signal power at the intended receiver, what I'm saying, which is denoted as P suffix R. Okay, so to hide the presence of the signal from receivers that are in the vicinity of the intended receiver. Okay, so the signal is transmitted at a power level such that this PR by PN should be less than 1. Means, or in other words, what we can say, the average received signal power at the intended receiver should be much less than the average noise power, okay, in the bandwidth of W. Then only it is possible to hide the presence of the signal, okay, from other receivers which are there in the vicinity of the intended receiver. Hope you are understanding what I am saying. Hello.
Yes, sir.
Yeah, so that is what about the low detectability signal transmission. I started with what I said here. the message signal will be transmitted at very low power compared to the background channel noise and the thermal noise, which is generated at the front end of the receiver, I said, right? Then I said, what is the bandwidth occupied by the spread spectrum signal? Then what is the power spectral density of the additive noise? Then how do we find the average noise power in the bandwidth W? So which is W into N naught. Then the average received signal power at the intended receiver is denoted as PR. Then what I said, what is the condition to meet that the means to hide the presence of the signal from the receivers in the vicinity of intended receiver, right? So that is what the received power, that is the average received signal power, should be less than the average noise power. Then only I will be able to hide my signal in the presence of or in the vicinity of the intended receiver. Okay, so the intended receiver can recover that weak information signal from the background noise with the aid of what? The processing gain and the coding gain. So which I discussed in the yesterday's class, right? So processing gain is what it is denoted as. So we can equate for processing gain in with many parameters, right? I said it is TB by TC, or it is also known as W by R, right? And even I think it is related with respect to signal power and the interference power also, right? Then how it is possible to detect such a low power signal is because of these things, because of the processing gain and the coding gain. The intended user will be able to detect such a weak signal even in the presence of noise. So any other receiver, okay, which is not having a knowledge of the pseudo noise code sequence, is unable to take the advantage of this processing gain and as well as the coding gain, right? So that is the basic idea here. What I wanted to say is how uh, it is possible to detect such a low power signal by a intended receiver, even if the signal is there in the vicinity of other people also. That is because of what? Because of the processing gain and coding gain, which is known to the uh, intended receiver. Okay, other receiver or other user will not be knowing the or having the knowledge of the pseudonoise sequence. So because of that, they will not be able to get the advantage of this processing gain and coding gain. Okay, so the transmitted signal has a low probability of being intercepted, uh, and that is why it is called a LPI signal. So LPI signal means low probability of being intercepted. Okay. Yes, hope you could catch the point. So what is the key point here? You need to take it. Any one of you can say. Yes, my dear students. What is the key understanding with respect to this low detectability? Yes, low detectability signal transmission. What is the key understanding here? Only the intended receiver or user will have the knowledge of the pseudo noise code. With that, he will be able to take the advantage of processing gain and coding gain to detect the low power signal in the vicinity of other unintended users also. Okay, because other users will not be having the knowledge of the pseudo noise code, hence they cannot take the advantage of the processing gain and the coding gain, hence they will not be able to detect such a low power signal. But the intended receiver or user will have the knowledge of the pseudo noise code, so with that he will be taking the advantage of the processing gain and the coding gain to detect such a low power signal, right? So that is why it is called as a low probability of being intercepted signal, LPI signal. Okay, yeah, here I think one more example with respect to this understanding. Just have a look. I think I want someone to read. Yes, who will read this? Yes, just for reading. I want someone to read this problem. If not answering, at least people can read now.
Sir, I'll
Hello,
read. I'll read.
Ananta. Read up.
A DS spread spectrum signal is designed so that the power ratio PR by PN at the intended receiver is 10 to the power of minus 2. If the desired EB by N naught equals 10 for acceptable performance, determine the minimum value of the processing gain.
Yeah, thank you, man. So, hope people have understood the question. So, here what is given, a direct sequence spread spectrum signal is designed. Okay, a direct sequence spread spectrum signal is designed so that the power ratio, what I said, PR by PN, right? PR is the what? Average received signal power. PN is the average noise power in a bandwidth W, right? And the intended receiver is 10 power minus 2. So that is the value of power ratio at the intended receiver. If the desired EB by N naught, so it is nothing but interference, right, which is equal to 10 for acceptable performance. So determine the minimum value of the processing gain. Okay, so we need to find out the value of processing gain. That is the minimum value of processing gain, so that the intended receiver is able to detect such a low power signal. Okay, so if the intended power is having a processing gain of so and so value, then with these parameters you will be able to detect that signal. So here as a solution, what I've given is, I said that this EB by N naught can be written as, I think yesterday also I discussed about this expression, right? So I again taken it here. So EB by N naught, EB is what PR into TB I said, right? So PR into TB by N naught I can write. Then, yes, of course, TB is equal to what? So LC, that is LC is equal to TB by TC we say, right? So TB is equal to LC into TC I can write. So that is what is substituted here. So TB as LC into TC. With respect to that, I have written here PR into LC into TC divided by N naught. Okay. So energy is power into the bit duration. I expressed this TB in terms of LC into TC because I know what is LC. LC is equal to TB by TC. So TB is equal to LC into TC. I have written here. Then, yeah, of course. So this TC is equal to 1 by W, or I can say W is equal to 1 by TC. Okay, so W is a bandwidth, right, of the spread spectrum signal, which is equal to 1 over TC we say. So that is what is substituted here. If I substitute TC as 1 by W, so it is rewritten as what? PR divided by W into N naught, okay, into LC. Okay, hope it is clear. Then I said W into N naught as PN, that is average noise power. So it is written PR by PN into LC. Okay, my goal is to find out the value of LC. LC is a processing gain. Okay, and he has given the value of PR by PN, so which is equal to 10 power minus 2, right? And even he has given the value of EB by N naught, which is 10. So I can find out easily the value of LC. So this is the beauty of relations, mathematical relations in this spread spectrum communication system. So as I said, it is basically developed for military communication, right? So how do they relate and how these equations comes is very important. Okay, so directly looking at the problem, you will not be able to say, okay, I can use this equation directly. Okay, you have to think about that. So finally, what you need to keep in your mind is EB by N naught is equal to PR by PN into LC. So these two things are given. PR by PN is given, EB by N naught is given. We need to calculate the value of LC. Hope I think that you will be able to do now. It is done also. I think people should be able to understand that. Okay, so EV by N naught is 10 and PR by Pn is 10 power minus 2. Okay, so if I substitute that, I can say what is LC. Is it LC is 1000? Is it correct what I have done?
Yes, sir.
Yes, sir.
Yes, please see, problem is very simple. Okay, see, even it will not take 2 minutes also to solve this. Only thing is you should know how to relate this processing gain, EV by N naught and PR by Pn. But you don't have to remember or add all these things. So you should know ultimately how EV by N naught and PR by Pn and the processing gain are related. Okay, so EV by N naught is equal to PR by Pn into LC. So two values is given. EV by N naught is given, PR by Pn is given. You can calculate what is the value of LC. Hope it is clear. Yes, shall I proceed to the next one?
Yes, sir.
Yeah. So before I take up the next one, just let me spend 2 minutes. Just yes, voluntarily, who can just sum up this concept, low detectability signal. So before I call your names, on a voluntary basis, people should come forward and can sum up. Already I have indicated, no, overall, not at all active in the class. Bharti is there. Bharti. Yes, Bharti. See where this fellow might have gone. Chandrika Murthy has left. So now I think they are understanding whom this fellow will call. What about Abhishek Reddy? Abhishek Reddy.
Sir,
Yes, man. Can you just tell me your understanding about that low LPI signal? No probability of intercepted, or whatever
yes,
you
sir.
have understood, whatever. So I thought so far about that application, low detectability signal. Yes, Abhishek Reddy, quickly. If you are able to say, you can say yes. Otherwise, you say you need time.
Sir, it is developed for mainly usage of military application.
That is all fine, man. Now you tell with respect to this application, low detectability signal.
Sir,
See
I
what is
need
it?
time in 1 minute. I'll
You
tell.
need time. So you should know. My request is be attentive. Okay. See, it is not that difficult to grasp the concept here. Yes, similarly, other students, I will take up from my side later on. Yes, what about Diksha? Diksha? Yes, Diksha Misra. No, not talking. What about Swag? Swag. Swag also not ready to talk. Then Aditi. Aditi. No, Aditi. Bharti did not talk. Okay. What about Chandan? Chandan. So all will be alert at 9:25, I think. Hmm? Yes, Ram Sai. Ram Sai.
Yes, sir.
Can you just tell me your understanding? Yes, Ram Sai. You say yes sir, no man. Do you need time?
I need time.
You want time. Fine. At least at the end of the class, you should be able to. Okay, even Abhishek Reddy, you ask him time now. I expect you to answer at the end of the class. Okay, what about Danya? Danya,
Yes, sir.
yeah, can you tell me your understanding about this low detectability application? Yes, be fast, ma. Low detectability signal.
Sir, I'll tell at the end of the class, sir.
Okay, fine. Fine, at least you are able to say that. Fine, good. Then Gautam Hegde. Gautam Hegde. Yes,
Sir,
Gautam Hegde. Is it possible to say your understanding about the first application? What I discussed now? Yes, man. Gautam, be fast. I'm unable to hear you. Okay. Okay, what about Girish? What meant Girish?
Yeah.
Uh,
Sir,
yeah, I asked a question. You should be able to answer.
so the signal is transmitted at a very low power.
Uh,
So it's related to background channel noise and thermal noise.
okay, whether that signal power will be less than, much less than that channel noise and the thermal noise,
And
or is it more than
less,
that?
less, sir.
Less. Okay, very good. Then,
So the receiver, which having the technology of pseudo noise coding, will gain the advantage by processing gain and coding gain.
okay,
So the receiver would don't have this technology, so they cannot take advantage of this
very good, man. Very
technology.
good. At least you have captured that point. I'm happy. Very good. So, yes, rightly what Girish pointed out is that the signal will be transmitted at very low power, which is less than the background channel noise and the thermal noise, which is generated at the front end of the receiver. So how the intended receiver will be able to detect such a low power signal, okay, in the vicinity of other users is the intended user will have the knowledge of the pseudo noise code which is used at the transmitter side. So because of that, he will be able to take the advantage of processing gain and the coding gain. So with that, he will be able to detect such a low power signal. Okay, the unintended users will not have the knowledge of the pseudo noise code, hence they will not be able to detect that signal. So that is the just see that is the only one key point. Okay, so rest all what just we say. How do we represent the average received power? How do we represent the average noise power? Okay, how they are related? Means mathematically we said PR by PN should be much less than one, and all. Then the key point to understand here is that how the intended receiver will be able to detect such a low power signal. Why not others? Okay, so it is just one line. If you are attentive, definitely you will be able to catch that concept. If you are not attentive, then definitely you will not be able to. Okay, okay. So Bharati is still not talking. I wanted to talk to him yesterday. Also, I called many times. He did not let me see when I will be able to talk to him.
Sir, I'm there, sir.
You are there. Oh, at least nice. You are responding now. I called many times. I think you might have gone to take something out. Maybe
No,
some
sir,
courier
I didn't
fellow.
know. I didn't know, sir.
What you did know? When I asked you questions, you did not respond.
No, sir, I didn't know the concept.
Then at least you would have told, no, like other people said, no, I will be able to answer your question at the end of the class. You
Yes,
did
yes,
not
sir.
respond. I thought some courier fellow might have come, so you might have gone to receive some
No,
parcel.
sir.
No, because that is the reason you have given so many times. Even yesterday also I called many times because I wanted to talk to you. You want me to tell now or you want me to talk to you personally?
I'll talk to you personally, sir.
Okay. Fine. Yes, let me continue. Hope you have understood this problem. Very simple, but definitely this type of problems will be asked, and many people will become panicked because they will not be knowing how to relate the parameters. Okay, it is very simple. I can relate this EV by N naught with respect to the average received power and the noise power and the processing gain. So two values are given, only we need to find out the processing gain. Fine. So with that, let me go to the next application. So which is wireless local area networks. Okay, of course, what I shown in the first slide, I may not be in the same order. So the second application is wireless local area networks. I hope you have some idea about this local area networks. You might have studied or studying in CCN, I think, okay, in this semester only. Fine. So to continue with this application, what I can say is this spread spectrum signals are used in IEEE wireless local area network standards like 802.11 and 802.11b. Okay, so of course this standards no, from IEEE 802.11a to almost I can say up to Z are there. Okay, so many versions of standards have been developed and named with the different capabilities. Okay, so as of now, let's just try to understand these are the two standards 802.11 and 802.11b. These two operates in the ISM band, so which is at 2.4 gigahertz. Okay, so you all know what is ISM, that is the unlicensed frequency band, right? Is it possible to say any one of you what is ISM stands for? I said it is an unlicensed frequency band. So there are two unlicensed frequency bands less than 6 gigahertz. One is this 2.4 gigahertz. So ISM stands for industry, scientific, and medical. Okay, for that application, it is used this, so which is a unlicensed frequency band. So these two wireless standards are used in this frequency band. Okay, so the available bandwidth in this frequency band is subdivided into 14 overlapping 22 megahertz channels. Of course, here they are using the concept of so many other things, but at least you should be able to say, understand. Let us assume that some amount of bandwidth is available. Okay. So what I said here is the available bandwidth is subdivided into 14 overlapping 22 megahertz channels. Okay, means each channel bandwidth is of 22 megahertz. They are overlapped. Even I can show the diagram. I will come back to that. Okay. In the IEEE 802.11 standard, an 11 chip Barker sequence is modulated. Okay. So this 11 chip, it is nothing but a pseudo noise code only. The name is different. So they call as a Barker sequence. Okay, for some particular pattern suggested by some scientist is known as that. So they are using 11 chip Barker sequence. Okay, which is modulated and transmitted at a chip rate of 11 megahertz. Okay. So here the chip duration means the value of TC will be equal to 0.909 microseconds. So I'm saying what is that chip Barker sequence used is here is this. So the 11 chip Barker sequence is 1 minus 1 1 1 minus 1. So here minus 1 is nothing but a 0. Okay. This is a binary sequence. Okay. 1 minus 1 1 1 minus 1 then triple 1 then triple minus 1. Okay. So this is what is the Barker sequence used in the 802.11 standard. And this sequence is desirable because its autocorrelation has the side lobes of less than or equal to 1. Why they have chosen this particular Barker sequence for this particular application is because this Barker sequence have the autocorrelation having a side lobes of less than 1. Okay, that is why they have used this Barker sequence. So compared with the peak autocorrelation value of 11. So the peak autocorrelation value is 11 and the side lobes having a peak value of 1. So because of that, this Barker sequence is preferred. Yeah. Then this Barker sequence means you should be able to visualize the block diagram of this spectrum. Right, the message signal is there. Right, first that will be spreaded by using a pseudo-noise code, I said. So what is the pseudo-noise code used here is a Barker sequence, and even that Barker sequence is also specified. After that, we do the modulation, right? So that is what done here. So the Barker sequence is modulated either by using BPSK or QPSK modulation. Okay, so when I use BPSK, it is possible to achieve some data rate. If I use QPSK, we are able to achieve some other data rate. So that is what is specified here. Okay, when BPSK modulation is used, it is with that 11 chip per bit. So it is possible to achieve a data rate of 1 Mbps. And when QPSK modulation is used, obviously you will be able to say with your understanding as of now. So obviously the data rate achieved by QPSK will be double the BPSK because we are able to send 2 bits per symbol, right? So with that we say here the QPSK modulation is used with 11 chip per symbol, that is 2 bits, right? So a data rate of 2 Mbps is achieved. So that is with respect to what 802.11 standard. Okay, then another one is 802.11b. Just we are saying here the application of the sequence, how what sequence is used and what is the type of modulation used and what is the data rate achieved with respect to this. So in case of 802.11b, this 11 megahertz chip rate is maintained, but the Barker sequence is replaced by what? The set of 8 chip waveform sequences. Okay, that a set of 8 chip waveform sequences are known as the complementary code shift keying. We call that as CCK. Okay, complementary code shift keying. So which will be viewed as the direct sequence spectrum modulation with multiple spreading sequences. So with the use of this CCK, what I said, that is the complementary code shift keying, possible to achieve a data rate of 11 Mbps. Okay, so this is what the difference between 802.11 and 802.11b. Okay, in case of 802.11, the Barker sequence is used with BPSK, possible to achieve a data rate of 1 Mbps. With QPSK, possible to achieve a data rate of 2 Mbps. But in case of 802.11b wireless local area network, that 11 megahertz chip rate is maintained, but the Barker sequence is replaced by what? Complementary code shift keying. So with that, it is possible to achieve a data rate of 11 Mbps. Okay, so this is all about the wireless local area network. That is the application of this spread spectrum in these two standards, 802.11 and as well as 802.11b. Okay. So with respect to application of wireless local area network, not much in-depth what we are going to understand how actually these signals are used and reliable communication is achieved. Nothing like that. What you need to understand here is what is the type of sequence is used, okay, and what is the type of modulation used. With that type of modulation, what is the data rate achieved? That much if you are able to grasp, that is more than enough. Okay. So the next one is, let me. Yes, I'm taking next two applications also. So if you have any questions to ask, you can ask. Yes, you don't have any questions? Hello? Yes, my dear students. I'm asking you people, do you have any questions?
No, sir.
It is understood. Hmm? I think, okay. So if that is clear, just then let me. Yes, is it possible, any one of you, about to say about wireless LAN? Yes, be fast so that we can take up the next application. Just wireless LAN. What is the thing I said? Key things to understand from that. Yes, I have given a question to everyone. Anyone can say. Wireless LAN. Can't? Yes, my dear students, please respond. No, not possible to say. Wireless LAN. What is that complex thing I said in wireless LAN? Yeah, I said there are two standards. One is 802.11 and another one is 802.11b, right? So, which are used in the ISM band, which is of 2.4 gigahertz, right? In that, what I said, uh, in 802.11, the Barker sequence is used, right? So you need to understand what is that Barker sequence. That is 11 chip Barker sequence is used, right? So with that 11 chip Barker sequence and with the type of modulation used, we are able to achieve 1 Mbps and 2 Mbps data rate. So I said when we will be able to achieve 1 Mbps and when we will be able to achieve a data rate of 2 Mbps. Right? So when BPSK modulation is used, during that time we were able to achieve a data rate of 1 Mbps. When QPSK is used, it is possible to achieve a data rate of 2 Mbps. That's all. And with respect to 802.11b, I said the type of Barker sequence used. So there the Barker sequence is replaced by CCK, right? So that is 8 chip, this one. So with that it is possible to achieve a data rate of 11 Mbps. Okay, that is what the simple understanding what I said. So I said we were not going so depth. Just I said what is type of modulation and used here. Yes, no other questions then. Shall I proceed to the next one? Hello?
Yes, sir.
Okay, man. People are not ready to discuss. They don't want to ask any questions also from their end. Hmm? Okay. Yeah, I think the next application is about the uh, code division multiple access. Hope it is. Yeah, I hope it is visible. See, now how the strength has increased. It was 40 plus. Now it has become 51. Okay, of course. Another 8 people have added because it is 9:30. Nah? So already I'm observing who is joining at the end, just before 10, 15 minutes, 10 minutes. Yeah. So let me discuss about this CDMA. Yes, I hope we're able to see uh,
Yes, sir.
this full slide.
No, sir.
You're not able to see full screen. Slideshow not able to see. Okay, man, fine. Yeah. So maybe you're having some idea about this multiple access techniques. So we say frequency division multiple access, time division multiple access, then code division multiple access. Like that, even OFDMA is also there. Orthogonal frequency division multiple access. Then we say, so they're all orthogonal multiple access techniques. Then at present, people are talking about NOMA, that is non-orthogonal multiple access. So just I will give in brief about even other than CDMA. Okay. So first, what I said, FDMA, no. So you all know what is FDM. That is a frequency division multiplexing, right? So how this multiplexing is different from multiple access, also you should be able to understand. Maybe you are aware how the multiple users are able to communicate with the base station. I hope you are able to visualize that. You're all using mobile, right? So multiple users in one particular cell will be able to communicate simultaneously with the base station. I hope you understand what I'm talking. Hello?
Yes, sir.
So here means with the development of this different cellular technology, they started with first FDMA, frequency division multiple access. Means different users will be able to talk simultaneously if they have been assigned different carrier frequencies. That is what the frequency division multiple access is. And next is time division multiple access has been incorporated in the digital system. So here, what I can say, multiple users can communicate with the same frequency but at a different time intervals. Okay, that is what is time division multiple access. Then CDMA means there is a code division multiple access. Here, multiple users can use the same frequency and same time slot, but each of them will be using a different code. Okay, so they will be able to communicate simultaneously with the same frequency, with the same time period by using different code. So that is known as the code division multiple access. Okay, just to give an analogy between this FDMA, TDMA, and CDMA, let us visualize that we have all have gathered in one party hall. Okay, so with the different parts of the country, you can think, or within India from different states, people have arrived for that party. Okay, you all know when people arrive from different states, they will be having the understanding of different languages, or some will have that understanding, some will not have, right? So some people means I may be only knowing Kannada, like that other people may be only knowing their mother tongue, okay, not any other common language. So let us assume that in case of each people to talk means let us again visualize that. So pair of people will be there in a big party hall. They can talk at their different tones. Okay, means that is the frequencies. What I can say, right? If they are able to talk at a lower frequency, means only those two pairs can hear, then there will be no interference with the other people, right? That is one possibility. That is known as the FDMA, what we can say. Another thing is time division multiple access means what we can say for each pair, we can ask them to talk for 1 minute. So others, all other people can listening it. Okay, so that is what the TDMA is. And a CDMA means all the pairs can talk simultaneously, okay, in their own language, and assuming that other pairs don't have the knowledge of other languages. Okay, that is what is the CDMA. Hope got my point. Hello.
Yes, sir.
Yes, sir.
So CDMA, you can assume that I said what they can, all pairs can talk simultaneously, right? But each pair will not have the knowledge of other pairs language. Okay, means Kannada, Telugu, Tamil, Hindi, like that. Okay, so I don't know Hindi, I will not be able to understand what the other people are talking. Similarly, other people don't know Kannada, they will not be able to understand what we are talking in that sense. Fine. So with that simple background and analogy, hope you all will be able to at least remember this analogy, even if not the uh, core crux of the technology. Okay, should be able to say at least in what way these multiple access techniques are different. Okay, fine. So that is what is done in here. So many direct sequence spread spectrum signals can occupy the same channel bandwidth, provided that each signal has its own pseudonoise sequence. Okay, so several users transmit messages simultaneously over the same channel bandwidth. So each transmitter receiver user pair has its own distinct signature code. The signature code is nothing but the pseudonoise code, right, for transmitting over the common channel, and that is known as the code division multiple access. Yeah, this is what the block diagram illustration of the CDMA. Hope you understand here. 3 different users are there, and each user information is represented by different colors. Okay, one is blue, then red, then is green, to say that there are of 3 different users, and for each user there will be a pseudonoise code, and that is also unique to each user, right? And it undergoes the spreading process. Then you hope you are able to see that when after the spreading process, how the bandwidth of the spreaded signal has been widened. Then the modulation will be done. Then it will be transmitted over the air. Okay, so like that, simultaneously, multiple users can transmit their information. So at the receiver side, okay, every receiver will be able to get the signal, right? So this is what is done here. So okay, of course, the type of receiver used is also mentioned here. That is a rake receiver, right? Then how do we get back to the concerned user, right? So then see, if I use whatever the code, desplitting is done, right? It's the first step. Then demodulation detector is done. So whoever is having the splitting code 1, that is pseudonoise code 1, he will be able to get back the information 1. Okay, that is a user information 1. Okay. So like that, for user information 2, then user information 3. Only the user information 1 will have highest power level. Okay, other users information will be having a low power. Okay, that you will be able to see with respect to this diagram. Yes, is this fine? Yes, my dear students, I'm asking, is this fine? This illustration of this figure.
Yes, sir.
So code division multiple access, actually it is introduced in 2Z, CDMA 1, CDMA 2000. You might have heard that. Maybe you were small kids during that time when they were released. Okay, in the year 2000, like that, they have released. Now it is 2021. Still, you might not have born also. Okay, if I understand, now you are at 20 or 21, right? Yeah. Okay. Yeah, to just get in detailed understanding about that, we can think of D1 of t, D2 of t, and so on up to Dn of t are the user information signal. So which will be spreaded by using the pseudonoise code C1 of t, C2 of t, and so on up to Cn of t, then modulated, then transmitted over the air. Okay, so when it is transmitted over the air, so there will be noise also added with the transmitted signal. Again, at the receiver side, what we do, first step is we multiply with the pseudonoise code, so that we will be able to despread the signal, then do the demodulation. So here one example is shown for D1 of t. That is why only C1 of t is used as a pseudonoise code here. So whoever is the C1 of t, you will be able to get back that signal, D1 of t. In the same way, it can be done for other users also. Okay, to get the information D2 of t, I need to use here C2 of t. D spread, then demodulate. So this is the what just correlator, right? Only the product modulator is shown, then further circuit will be there. Okay, so here, of course, FC only is written. Of course, the modulation technique will be different. Means different carriers will be there. Okay. Yeah, just to give a big picture about the application of CDMA. Here, I have shown one diagram with the cellular communication only. Hope we will be able to grasp this idea, this concept. I don't know whether is it visible clearly. I made big picture. Let me reduce the size. Yeah. So you'll be able to see macro cell, micro, right? Even pico cell. So all depends on the coverage area. Okay, how much each cell can cover. So depending upon the distance, we classify these cells as pico cell, micro cell, macro cell, and all. Okay, so macro cell coverage area will be larger. Micro cell will be less than that. Then pico cell will be much less than that. Okay, so just to get an idea how things are done. Fine. So let me try to explain the advantages of CDMA. So the major advantage of CDMA is that so large number of users can be accommodated if each user transmits the message for a short period of time. So it is relatively easy to add the new users or to decrease the number of users without reconfiguring the system. So that is the beauty of this CDMA. Okay, because there is a limitation on the number of users can be accommodated in case of FDMA and TDMA system. But in case of CDMA, as you said, we are able to accommodate large number of users. Okay. So to determine the number of simultaneous signals that can be accommodated in CDMA system, so this is what the procedure is. Okay, so since we are discussing with respect to CDMA, at least let us try to understand how do we find the number of simultaneous users that can be accommodated in case of CDMA system. So to understand that, so first assumption is, let us assume that all signals have identical average powers. Okay, all signals have identical average powers. So that is the first assumption. Then the second one is the received signal power level from each user is monitored at the central station, and the power control is exercised over all simultaneous users via the control channel that will instruct the users on whether to increase or decrease their power level. Okay, hope you are getting my point. First assumption is what? All signals have identical average powers. The second one is, as I said, the received signal power level from each user is monitored at the central station, and the power control is exercised over all the simultaneous users via the control channel that will instruct the users on whether to increase or decrease their power level. So with this assumption, now I hope you are able to get who is going to who is having a control over the transmission power of each user, right? How it can be increased or decreased. So that will be done by using control channel. So I think with that understanding, so just let me say how do we calculate that. So if there are n suffix u, okay, is the simultaneous users, means number of simultaneous users, I denote it by n suffix u. Okay, so n suffix u is the number of simultaneous users. The desired signal to noise interference power ratio at the given receiver is given by this formula. The desired signal to noise interference power ratio at the given receiver is PS by PN. So PS is the what? The signal power. that is the desired signal power, and Pn is the noise power, right? So Ps by Pn is equal to Ps divided by, so number of simultaneous users minus 1 into Ps. Okay, so here Ps will get cancelled, means I will be getting 1 by Nu minus 1, where Nu is, I said, number of simultaneous users. So here I have substituted the noise interference as, see, the number of users minus 1 into the desired signal power. Okay, so from this equation, what I can determine is, I will be able to determine the number of users that can be accommodated simultaneously. Means if they give what is the desired signal power and what is the noise power, right, then I will be able to find out what is the or the number of simultaneous users that can be accommodated in that particular system. Okay. So this is what the equation which you need to understand. The desired signal power to the noise power, Ps by Pn is equal to 1 divided by number of simultaneous users minus 1. So if you know that, then definitely anything they may ask. They may give the number of simultaneous users, they may give the noise power, they may ask you to calculate a signal power or any other parameter. Okay. So here let us assume that the pseudo-noise sequences used by the various users are uncorrelated. Okay, if there is a correlation, that is a different thing. If they are uncorrelated, let us see what is that. So interference from other users adds on the power basis only. So these are the two assumptions which we are making here. One is what? The pseudo-noise sequences used by the various users are uncorrelated. And second thing is the interference from other users adds on a power basis only. So with these two assumptions and this equation, so let me take up one example, I think. Yeah. So this example also has appeared several times in the question paper. You can give an attention and try to understand this. So this is where the problem we use to find out the number of simultaneous users. Yeah, I think I ask any one of you to read this problem. Yeah. Yes, hope everybody is alert. I asked a question just to read out this problem. Yes, Swag. Swag.
Yes, sir.
Can you read out this problem, man?
The
I'm
desired.
just asking you to read, man.
Yes, sir.
Ah.
Sorry, sir. My mic is.
Oh, your mic is not working. It is
No, sir.
working now,
My
man.
phone is spoiled, sir.
Uh-huh.
My phone is spoiled, sir.
But you're able to talk now.
Yes, sir. Yes, sir. It will break in the middle, but I'll try it.
Uh-huh.
Sir, the desired level of performance for a user in a CDMA system is an error probability 10 to the power minus 6, which is achieved when EB by N naught is equal to 20. Determine the maximum number of simultaneous users that can be accommodated in a CDMA system. If the bandwidth to bit rate ratio is 1000 and the coding gain is RC, D min is equal to, the minimum is equal to 4.
Very good, man. So without any break, you could read.
Yes, sir. Thank you. Thank you, sir.
Yeah, thank you, man. So try to understand this problem, what parameters are given, and what I just discussed in the previous slide. Okay. So there I said Ps by Pn is equal to 1 by n suffix u minus 1, where n suffix u is the number of simultaneous users. But earlier discussions will also help. Okay. Fine. So as I said, see here he has given what is the desired level of performance for a user in the CDMA system. Means he has given the error probability which is equal to 10 power minus 6. So this error probability can be achieved when this EB by N naught is equal to 20. Okay. So which is nothing but 13 dB. Okay. When the EB by N naught is 13 dB, it is possible to achieve an error probability of 10 power minus 6. So that is what is the performance of the CDM system. So he's asking us to find out the number of that is maximum number of simultaneous users that can be accommodated in this CDMA system if the bandwidth to bit ratio, okay, bandwidth to bit ratio is 1000 and the coding gain is RC into D minimum H is equal to 4. In terms of dB, it says it is 6 dB. Okay, so of course, I don't know how many of you have understood and remembered that equation. Yesterday, last slide, I said how EB by I naught is related with respect to coding gain. So here nothing, I said EB by I naught is equal to here it is what W by R is, what W by R is nothing but the processing gain, okay, divided by NU minus 1 into this coding gain, RC into D minimum power H. So he has given the value of EB by I naught or EB by N naught is same as I said, which is equal to 20 as given, okay. So I need to solve this expression for NU. Then I can find out, because I know what is W by R, okay, because he has given bandwidth to bit rate ratio, means W by R is 1000. So W by R I know, and even this value is given RC into D minimum H, which is equal to 4, right? So I will be able to easily find out what is the value of NU. So if I solve for NU, then what I can write, NU is equal to W by R, right? W by R divided by EB by N naught into this RC into D minimum H plus 1. This minus 1 means we can take this NU minus 1 to this side and EB by N naught to denominator side. I hope you do that cross multiplication. Then you can say what is NU. It's a simple this one, right? So we know this W by R is 1000, right? And EB by N naught is 20. So here while substituting, you need to take either ratio or only dB. It should be of common unit. If it is in dB, you need to add. If it is in ratio, directly substitute and say what it is, right? So it is 1000 by 20 into RC D minimum H is 4 is given, right? So if you substitute those values, so 1000 by 20 is how much? Yes, 1000 by 20.
50.
Huh?
50.
50 into 4, because RC D minimum H is 4, right? So 50 into 4 is
200.
200 plus 1 is 201, right? So hence we say the number of simultaneous users that can be accommodated with this specification is 201. Okay, hope is this clear? So only thing is, see what I said in the previous slide here, and maybe based on the parameters specifications what they give, we need to think about this on, since already it is given here. I think you can try to understand this equation. Okay, EB by I naught will be in this fashion. Okay, maybe I think if you go back and see what I written for EB by I naught, then it is just substitution only then. Okay, fine. So this is all about CDMA. Okay, one numerical example is solved, and I said what is that concept, CDMA. So next one is multipath. I said na multipath. So let us try to understand what is that. Okay, so this will be your the last application of this spread spectrum communication. Yeah, so we all know that the wireless channel. Okay, so hope you all able to see this diagram. So this is the base station, okay, which will be radiating the electromagnetic signal, and of course this is the receiver. The fellow who is traveling in a car is communicating with his maybe some friend or somebody. right? How he will be able to receive the signal, right? So from the base station, the signal will be reaching the receiver in a different paths, right? So this is one path. This we call it as a line of sight path. Hope you are able to see my cursor movement, right? So one is this line of sight path, and another one is what? It is going hitting this building and then reflecting back, right? Then another thing is it is going and hitting some what we call this what we call these things, signboards, right? So it will be hitting the signboard and then reaching the receiver, right? Even just it is an illustration like this, many other things will be there, even trees will be there, okay, hills will be there. So between the transmitter and the receiver, there will be no one path in case of wireless, okay. So the signal received at the receiver will be traveling through different paths. So what happens here when the signal is transmitted? So here is shown an example, okay, at this instant, okay. So it will be the same signal will be received at the receiver side through different paths, right? At the receiver side, maybe there will be some delay between one path to another path, right? So that is what is shown here, signal at the receiver. And as you all know, as the signal travels through the channel, definitely it will be getting attenuated, okay. That is why the amplitude of the signal is also shown less, okay. Maybe of course the line of sight signal will have a highest signal strength compared to other path signals. So that is what is shown here, and there will be overlap of those signals also, because we are receiving the same signal with different magnitude, right, at the receiver through different paths. So that is known as the multipath. Okay, here what happens, actually we wanted to receive the actual signal, right? But we are receiving the original signal, right, multiple times. So when we are receiving the original signal multiple times with overlap in their duration, what happens? It will be a noise. It looks like a noise, right? You will not be able to hear it properly. So then how do you overcome this problem? Okay. Means this multipath is having positive effects also, and it is having negative effects also, okay. So you understand what is the positive effect and what is the negative effect of this concept. Let us see. So signal can take many different paths between sender and the receiver due to these processes: reflection, scattering, diffraction, and all, which are there in the nature, right? Because so what are the positive effects of this multipath? Let us. So it enables communication even when the transmitter and receiver are not in line of sight conditions. Okay. So that is one positive thing. So it allows the radio waves effectively to go through the obstacles by getting around them. Thereby, it will increase the radio coverage area. Okay, due to this reflection, scattering, and all, it is possible to extend the range of communication. That is a positive effect of this multipath. Yeah. So, what are the challenges here? Yeah, that I said already. When the signal is traveling from transmitter to receiver through different paths, so it will be received at the receiver side multiple times with overlap, so that leads to a distortion, okay. So how do we overcome that is a challenge, okay. So the RF signal travels through multiple paths. So RF channel is characterized by this delay profile. I think all these things will be able to get better understanding when we are discussing about wireless communication, WCLTE. There in detail we discuss about what is delay spread, okay, what is coherence bandwidth, and all those things. So at least as of now, what you should be able to understand is, so this delay spread means, see, the transmitter is transmitting the symbol, okay. Let us assume that is one rectangular pulse. See the duration from where to where it is, right? From here to here it is there, right? So this we call as the delay spread, and this is what the symbol duration. Okay, here capital T is written. This is what the symbol duration, and that delay spread is this much, right? So this delay spread has to be less than the symbol duration. If the delay spread is less than the symbol duration, then there will be no interference at the receiver side. Okay, then there will be no inter-symbol interference, what I can say. So if the delay spread is much greater than the symbol duration, then definitely there will be overlap of the present and previous symbols. With that, it leads to interference. Okay, so as of now, you just understand that much. We'll have a detailed discussion about this inter-symbol interference and all in the upcoming lectures. Hope you got my point. So delay spread means the transmitted signal will be received at the receiver side multiple times through multiple paths. So there will be extension of that, right? Present pulse, right? So that duration has to be less than the symbol duration. Then we say there will be no inter-symbol interference. If the symbol interval is greater than that delay spread, right, then there will be no issue. If the delay spread is greater than the symbol interval, then there will be a problem. Okay. Okay. ಇದನ್ನ ಇವರು ಜೋಶಿ ಮೇಡಮ್ ಇದರಲ್ಲಿ ಸೇಮ್ ತಗೊಂಡ್ಬಿಟ್ಟು ಇಲ್ಲ ಒಂದು ಕಡೆ ರಿಸೀವ್ಡ್ ಅಂತ ಹೇಳಿ ಮಾಡ್ತಾರೆ ಅನ್ಸುತ್ತೆ ಮೇಡಮ್. ಹಾಂ ಜೋಶಿ ಮೇಡಮ್ ಗೊತ್ತಾ ಎಲ್ಲಿ Yeah, I think so. These are the negative effects of the multipath. So one is time dispersion, or we say delay spread. So as I said, the signal is dispersed over time, right? Due to signals coming from different paths of different length. So that we call as a delay spread. So that leads to what? Interference, right? Means it causes interference with the neighboring symbols. That we call it as an inter-symbol interference, I said. Okay, so the multipath spread or a delay spread is equal to, just an example I've given here, longest path of say T1 minus shortest path of T2 by C. So that interval duration divided by the speed of light. So if I take for 5 millisecond symbol duration, okay, a 1 millisecond delay spread means it is about what, 20% of this, right? So that leads to an inter-symbol interference, means there will be overlap of that. So the signal reaches the receiver directly, and there will be phase shift also. So due to that, reflections. So the distorted signal, depending on the phases of different parts, that we refer as Rayleigh fading. So these are all statistical models are there for channels, Rayleigh, Nakagami, and Racine distribution and all. So let us not have that much detailed here. So that much detailed understanding is not required as of now. At least you should be able to grasp the idea of what is multipath communication. Okay. Yeah. Yeah, I think I have done more about this. Even how do we overcome that problem and all, I said about the OFDM. I don't know how much you will be able to grasp this idea. Fine. So let me at least tell that. So what I am saying here is frequency selective channels. So this we say when the signal bandwidth is larger than the coherence bandwidth of the channel. So if the signal bandwidth is greater than the coherence bandwidth of the channel, then we say it is a frequency selective channel. Okay, so to overcome this multipath effect, there are two approaches. One is the use of OFDM, that is orthogonal frequency division multiplexing. Okay, OFDM is that modulation techniques. So here what we do in case of OFDM is we are going to subdivide the available bandwidth into n sub-channels so that the bandwidth per channel, that is W by N, is much less than the coherence bandwidth. Okay, I repeat once again what I said. We are going to subdivide the available bandwidth into n sub-channels so that the bandwidth per channel will be less than that coherence bandwidth. Then each sub-channel is a frequency non-selective, and the signal in each sub-channel will satisfy the condition that the symbol interval, this t, will be much greater than the delay spread, right? Then we will be able to say the inter-symbol interference is avoided. So this is one approach. Another approach is what? So design the signal to utilize the entire signal bandwidth and transmit it on a single carrier. So that is another approach. Okay, we need to design the signal to utilize the entire signal bandwidth and transmit it on the single carrier. So this is what the approach of this spread spectrum. Okay, so here the channel is frequency selective and the multipath component with the different delays, which is known as 1 by W or greater than, becomes resolvable. Okay, this is how it's done to overcome the multipath. Yeah. So as I said, no, the second approach. The first approach is OFDM. Second approach is that. What is the second approach? I said we need to design a signal which will utilize the entire signal bandwidth and transmit it on a single carrier. That makes the what? Multipath component with differential delays will be greater. So it is possible to resolve that problem. So this direct sequence spread spectrum is an effective way to generate the wideband signal, right, for resolving the multipath signal component. So this is how the spread spectrum will come into picture in avoiding the inter-symbol interference or in case of multipath. So by separating the multipath components, it may reduce the effects of fading. Okay, so what we can say is the inter-symbol interference can be avoided if we are willing to reduce the symbol rate. Symbol rate is 1 by t. T is the bit duration, right? Such that the symbol interval is much greater than the delay spread. Okay, so where Tm I said multipath spread of the channel or delay spread. So we are going to use this direct sequence spread spectrum signal with a bandwidth W to resolve this multipath problem. So this is how I say the direct sequence spread spectrum plays a role in resolving the problem of multipath. Okay, so of course whatever the content is there in this slide is from your textbook only. Of course, a few things I've taken from outside. That's for understanding these things. Okay, I don't know. This is from your text only. To what extent it has reached, God only knows. People should say. Yes, any questions to ask, you can ask about either CDMA or about this multipath communication over channel with multipath. So out of these 4 applications, definitely they will be asking any 2 applications for 8 marks like that. So there will be one question on this, I can assure you that. Okay, so try to understand all these 4 applications properly. I hope I told what is the key concept in each of the application. Yes, is that fine? Yes, my dear students. Everybody is become silent. I don't know why. Hello? Nobody is ready to talk.
Yes, sir.
Is that fine? So let me take up the next topic. Yes, hope we're able to see this. Yeah, I think now we're able to see. So let us try to understand about this pseudonoise sequence. Okay, how do we generate the pseudonoise sequence and what are its properties? Then, similar to that, there are some other codes also like gold codes and Kasami sequences, right? In addition to that, few more codes like wash code and Hadamard sequence. Okay, so which are all used in different parts of this spread spectrum system. Okay, so this pseudonoise sequence will have good autocorrelation and as well as cross correlation. Okay, and the code set is small, means the length of a pseudonoise code sequence is limited. So that is what I wanted to say in one word. So sorry, before I take up in detail about these things, let me just say what is what. Okay, this gold codes and Kasami sequences are derived from the M sequences, means that is the pseudonoise sequence with similar correlation properties and a large code set. So that is what the difference. Though these gold codes and Kasami sequences are derived from the M sequence, with what? With similar correlation properties and larger code set. And these wash codes and Hadamard sequences are having a zero correlation between codes when aligned and the cross correlation non-zero when time shifted and fixed spreading factors. So these are some of the key characteristics of this wash codes and Hadamard sequences. It has zero correlation between codes when aligned. Okay, and it has cross correlation is non-zero when time shifted, and it has a fixed spreading factor. Okay, means codes of different lengths are not orthogonal here. Okay, that is the main key things which we need to understand about these codes. Okay, hope you have got some idea. So these are the three different codes. One is what? Pseudonoise sequence. It is also known as M sequence. So these pseudonoise sequences will have good autocorrelation and as well as the cross correlation, but the code set is small. Gold codes and Kasami sequences are derived from these M sequences with similar correlation properties and a large code set. Okay. The third thing is the wash codes and Hadamard sequences have the zero correlation between the codes when they are aligned and have cross correlation with non-zero when they are time shifted. Okay, and these codes have a fixed spreading factor. What I mean to say is codes of different lengths are not orthogonal. So let us try to understand how do we generate this pseudonoise sequence and what are its properties. Okay. Yeah. So as I said already, you have done the experimentation. So it is sequence of shift registers. Okay. So a pseudo noise or pseudo random or pseudo noise, both are same. So PN sequence is a code sequence of ones and zeros with certain autocorrelation properties. So let us try to understand those properties in the coming slides. First, let us try to understand how do we generate this, right? So this binary pseudo noise code sequences have a maximum length shift register sequence. That is why it is called M sequence. Okay. So this M sequence has a length. Okay. So the length of the sequence is related with this relation. So L is equal to 2 power M minus 1 bits, where M is the number of shift registers used in the circuit. Okay. Means if I have 5 shift registers, then 2 power 5 is how much? 32. So 32 minus 1 will be 31. So that will be the length of the PN sequence. Okay, if I am using 3 shift registers, then 2 power 3 is 8. So 8 minus 1 is 7. So the length of the M sequence or PN sequence will be 7, we say. Okay. So let me take the example. Hope you are all able to see this diagram. So with respect to the previous, what we take feedback at certain shift register output, then we do the modulo 2 operation, that is XOR operation, then we give it feedback. Okay. So let me take this one example, then we'll be able to understand how do we get that sequence. So here I'm using 3 flip-flops. Okay. Flip-flop 1, flip-flop 2, and flip-flop 3. So output of each flip-flop, I'm calling it as what? This is X1. Okay. Then X2, then X3. Okay. So this is my output sequence, X3. So here what I have done, I have taken output of flip-flop 1 and the output of flip-flop 3. That is X1 and X3. I am doing the modulo 2 operation. Okay. So I am doing the XOR operation. The XOR output will be given as input to the first flip-flop. So this is how in this loop. Okay. So now let us try to understand how this circuit will be able to generate the output sequence, that is PN sequence. Okay. Here certain assumptions we need to take. We cannot take the initial state as 0. So all zeros. Right. If I take all the states of these flip-flops are 0, then what happens? 0 XOR with 0. It will be 0 only. So it will be in that zeros only. So you will not be able to get any other sequence. That is one thing. Okay. So let us assume that the initial condition of this flip-flop is what? 1, 0, 0. That is what I have written first here. X1, X2, X3. Hope you are able to see this table. Right. So output of flip-flop 3, that is X3, is my output sequence. Right. So I have taken the initial state of this as what? 1, 0, 0. Okay. So I will be applying a clock pulse. So for first clock pulse, what I get, it will be shifted by 1 bit, right? So what happens? Whatever 1 is there in the first flip-flop, it will move to the second flip-flop. So whatever there in the flip-flop 2, that has been moved to flip-flop 3. Right? Means first state is what? 1, 0, 0. Right? So for that, I am getting output sequence as 0. Means X3 output is 0, right? So when I apply the clock pulse, what happened? Whatever there in flip-flop 1, that has been shifted to flip-flop 2. Right? And whatever there in flip-flop 2, that has been shifted to flip-flop 3. Right? Then, say I'm taking output of flip-flop 1 and output of flip-flop 3, I am doing the modulo 2 operation. Means here X1 is 1 earlier, right? Then X3 is 0. So 1 XOR with 0, it will be 1, right? So that 1 will be fed into the flip-flop 1. So that is why I am getting the second as what? 1, 1, 0. Okay, 1, 1, 0. So whatever the output of flip-flop 3, that will be my output sequence. No? That's why I written here 0. Okay. So next what happens now? See, output of the flip-flop 1, that is X1, here it is 1, right? And X3 is 0. So 1 XOR with 0, it will be what? 1, no? So that 1 will be fed to the flip-flop 1. So now this has been shifted by 1 bit, right? So it becomes 3 ones. Okay, so 3 ones. And what is the output of flip-flop 3x3? That is 1. So that will be my output sequence. So next clock pulse, what happens? So again, x1 XOR with x3. So x1 XOR with x3 means 1 XOR with 1. It will be 0. So that will be fed to the flip-flop 1. That is why I am getting 0, 1, 1. So output of x3 is 1. So it is written here. Right? So for next clock pulse, what happens? Again, 0 XOR with 1, it will be 1. So that will be fed to the flip-flop 1. So 1, 0, 1 I will be getting. Right? So whatever x3 is there, that will be my output sequence. Hope you understood how do we get this. First, we need to assume the initial condition. What is that initial condition I said? For this, I have taken 1, 0, 0. Okay. With that, what is the output of flip-flop 3? That is my output sequence, right? So x3 is 0, that is why I written here 0. Then when I apply a clock pulse, what happens? The bits get shifted, right? And here what I am doing the modulo 2 operation. That is x1 XOR with x3. What is the value of x1 here? It is 1. And x3 is 0. So 1 XOR with 0, it will be 1. So that 1 will be fed to the flip-flop 1. So I am getting 1, and whatever there in x1, that has been shifted to flip-flop 2, right? So 1, 1, 0 I get. So x3 as my output, right? Then for the third clock pulse, right, again this 1 XOR with 0 will be 1. So now it becomes 1, 1, 1. Yes, it is just shifting for every clock pulse. And what I am feeding as input to the flip-flop 1, I am taking the XOR operation of x1 and x3. So why I took the output of flip-flop 1 and output of flip-flop 3, and I am doing XOR operation, that is the design this one for this. Okay. Even I can take output of flip-flop 2 and output of flip-flop 3 like that. So that depends. There is a logic for that. We will have a discussion about that. So first let us try to understand this. Hope this point is clear. I hope you all might have understood. For the first clock pulse is this. So second clock, third, fourth, fifth, sixth, seventh. After that, again it started repeating. See, right? So it keeps shifting, right? And the output of this XOR will be fed as an input, right? After 0, 0, 1, again I will be getting 1, 0, 0. So means what I can say, here I am using 3 flip-flops. I can say the length of the pseudo PN sequence or M sequence will be what I said, 2 power M minus 2 power M, then minus 1, right? So here M is 3. So 2 power 3 is 8, 8 minus 1 is 7. So the length of the M sequence is 7 bits. So this is what the output of my PN sequence I can say. That is 00, 111, 01. Yes, hope you understood this point. Okay,
Yes,
here
sir.
why I have taken the initial state as 100, it is an arbitrary. You can take any other state. Out of these 7, you can start writing with any state. It is not that you should start with 100 only. Okay, it is taken arbitrary one. Initial state is arbitrary one. Okay, so that is what is written here. Any of the other 6 states could serve equally well as in the initial state. You can take initial state as 110 also, or 111 also you can take it as initial state. So from that point it starts. So very simple operation. Hope you all will be able to understand this, how we get the pseudo-noise sequence. So is that point is clear? When the value of means when the, it depends on the M sequence length or pseudo-noise sequence length, it depends on the number of shift registers used. Okay, minus 1, that is L is equal to 2 for M minus 1. So here I have taken the initial state as 100. You can start with 011. So accordingly, I hope people will be able to write. So I asked 7 people to write with 7 different states, at least for this example. Okay, Bharati, Ananta, Aditi. Hope people are noting their names. Then Abhishek Reddy, then Girish. Is that 7 people? There are 6 people take already one set of sequence I told. Okay, then Chandrika or Murthy. Who is that? First one I said. Whose name I said first? Hello. So if not possible to do it at home, I think you can start explaining here only. Yes, Aditi, is it possible to say if the initial state is 111, how does it functions? How do I get the sequence? Hope Aditi is there. Yes, Aditi. Yes, Nagaveni, is it possible for you to say? Nagaveni. Yes, what about Sovik? Sovik Roy. Sovik. Subiksha. Yes, Subiksha. So all have already taken it granted. They are not able to respond. Tipana.
Yes, sir.
Can you just tell with the initial condition as 011 man, how do I get this table? If I take the initial condition as 011.
Yes, sir. 1 and 0 are 0, sir. And 0 and 0 is 0.
What man? 0. If I take initial condition as 011, what is the next state?
0, sir.
Next state, man. What 0? If I take initial state of the flip-flop as 011, what will be the next sequence?
101, sir.
101, right? See, it is very simple to understand. Just shift, right? XOR of output of those two flip-flops, that will be fed as input to that flip-flop. Then it keeps shifting, right? So 011, if I take as initial state, the next state will be 101. The next will be what? 010. Next will be 001. The next will be 100. Next 110. Next 111. Then it will be 011. Right? It keeps like that. Okay, then fine. Let me stop with this today. I think before that, just let me say all of you should note down. I will not again put in GCR. You people should be, take this circuit. Okay, all of you. I will just say the assignment. You people means it is with 4-bit, right? So I expect with 4-bit, so many 2 power 4 minus 1. So 15 different states. So totally 64 students are there. Okay. So at least in terms of groups, people should not copy. So what I wanted to do is each one should write with a different initial state. Okay. So yes, note down this diagram. You all can take the screenshot of this. I will put the question this in GCR, but I will not give the circuit. Okay. Only initial state also I am not representing with this 4 flip-flops, and even the feedback also can be taken. I think you take the same feedback. Okay. X3 and X4 XOR and fed as input. So you people should be able to write the table and say what is the PN sequence. Okay. I expect this answer by Friday. because tomorrow I don't have class, right? Friday, I expect you people to say. It should be uploaded in the GC